Hi, this is Wendy Lightheart, and for this lesson we're going to be learning how to divide polynomials. So to divide polynomials, there's a few rules of exponents we're going to need to learn. And the first one is the quotient rule. So this says that when we're dividing an exponential expression with the same non-zero base, then we subtract the exponent in the denominator from the exponent in the numerator. So notice here that in the general rule, we see we have the base of b being raised to the m in the numerator, and the same base in the denominator being raised to an n. And so to simplify that, this rule says that that'll become a single base of b, and the exponent on that base we get from subtracting the exponents. And remember that it will always be in the order of top exponent minus the bottom exponent. So in this case it would be m minus n. And we use this difference as the exponent on that common base. So let's use that rule to divide x to the 7th by x squared. So notice that the bases are the same, so that's important because they have to be the same to be able to apply the rule. So the quotient rule says that this will simplify to a single base of x with an exponent that we get from subtracting the exponents, and it's always top minus bottom, so in this case it will be an exponent of 7 minus 2. And of course that difference can be simplified, so our final answer is x to the 5th. Here's another example. This time our base is a number instead of a variable. But it doesn't matter, the quotient rule applies just the same. So the quotient rule says that as long as the base is the same on the top as it is on the bottom, so that we have a base of 5 in both cases, the top being raised to the 4th power and the bottom being raised to the 1, then this will simplify to a single base of 5, and the exponent on that base we get from subtracting the exponents. And remember, it's top minus bottom, so the exponent we will get from doing the subtraction of 4 minus 1. And note that we do not change the base. So whether the base is a variable or a number, it doesn't matter. The base will stay the same, and we'll just simplify that to that single base and then subtract the exponents to get the exponent on that base. Then we simplify as much as possible, and this is where it will differ from the examples where the variable is the base, because we can't simplify as much. But if we have a number for the base, then we can actually perform that calculation to simplify it one step further. So 5 cubed means 5 times 5 times 5, which is equal to 125. So we go ahead and do that one last step to simplify as much as possible. So to come up with another rule that we're going to need, we're actually going to see how the quotient rule can be used to kind of see how that rule comes about. So what if we had y to the 7th divided by y to the 7th? Well, we have the same base on the top as we have on the bottom, so we could use the quotient rule that says that this will simplify to a single base of y, and the exponent on that y will come from subtracting the exponents. But when we subtract the exponents, because they're the same, 7 minus 7, we end up with an exponent of 0. But we know that any non-zero expression divided by itself is 1. Like 5 divided by 5 is 1, 11 divided by 11 equals 1. And so y to the 7th divided by y to the 7th is also equal to 1, because remember that the y represents some real number. So we have some real number divided by the same real number. That's always going to equal 1. So we had y to the 7th divided by y to the 7th equals y to the 0, and we also see that it's equal to 1. So what that means is y to the 0 must be equal to 1. And that's how we get our next rule, which is called the zero exponent rule. So this rule says that if b is any real number, or of course an expression that represents a real number other than the number 0, then if we raise that expression to 0, the answer is always 1. And you could try this on your calculator, plug in any real number that you would like and raise it to the 0 power, and you'll see that you'll always get 1 as an answer. So let's look at a few examples to see how this zero exponent rule could be applied. So 5 is a real number, and if we raise it to the 0 power, then the zero exponent rule tells us that this will equal 1. Here's another example. This time we have an expression being raised to the 0. And so the 2 times x times y is our expression, and the whole thing is inside parentheses, so that tells us that we're raising that entire expression to the 0 power. So that's really just some real number being raised to the 0 power, and so by using the rule we see that we get 1. This next example is very similar, but notice that the parentheses are gone. So how does that change things? Well, the parentheses will group everything together so that you'll be raising the whole thing to the 0 power in that last example. But without the parentheses, that means only the y is being raised to the 0 power. So the exponent will always only apply to what's immediately to the left of it, unless there's parentheses to say that it applies to more than that. So we have 2x times y to the 0, and y to the 0 is just 1 by the zero exponent rule. So we have 2x times 1. 2x times 1 is just 2x. So that's why we get 2x as an answer versus the 1 that we got an answer in the last example. So the parentheses indeed do make a difference. Here's another example that has parentheses. So it's saying to take that real number -2 and raise it to the 0 power. -2 is just some real number, so again we apply the zero exponent rule and we see that we just get 1. Well, this next example, the parentheses are gone. So what is it that's being raised to the 0 power in that case? Well, only the 2 is being raised to the 0 power, not -2. So that can be a little tricky. So pay very close attention to whether you have parentheses or not. So we're raising the 2 to the 0 power, and that gives us 1. And so the negative sign is still there, giving us an answer of -1. Here's another rule that we'll need to use to divide polynomials, and this is called the quotients to powers rule. So we have a quotient, a over b, being raised to the power of n. So the rule says that when a quotient is raised to a power, we raise the numerator to that power and divide that by the denominator raised to that power. So we basically applied the exponent to both the top and the bottom, and then the parentheses are gone. So let's use that on a couple examples here. So here we have the quotient of 2 to x. So 2 divided by x is a quotient, and we're raising that to an exponent. So we need to use the quotients to powers rule. So the rule tells us to cube both the numerator and the denominator. So we do that first, and then we simplify if we can. So since the base of 2 is a number, we can actually perform that calculation. And 2 cubed means 2 times 2 times 2, so that equals 8. And then the denominator can't be simplified, so we're done. Here's another example where we have a to the 3rd power over b to the 5th power, and all that quotient is being raised to another exponent. So again, we need to apply the quotients to powers rule that says to square both the numerator and the denominator. And notice that in the numerator we have a power that we need to square. So a cubed needs to be squared. So we'll need to use that power to a power rule that you learned earlier, which says that we multiply the exponent. So we multiply the exponent of 3 times the exponent of 2 to get an exponent of 6 on the a. And similarly in the denominator we have b to the 5th being squared, so that's another power to a power scenario, so we need to multiply the 5 times the 2 to get an exponent of 10. And both those bases are variables, so that's as far as we can go as far as simplifying goes. Here's one that's a little bit more complicated. We still have a quotient to a power, so we apply that quotient to powers rule, which says since we're cubing a quotient, we need to cube both the numerator and the denominator. And notice in the numerator we have a product that's being cubed, so a product to a power. So that's another rule we have to use that we learned earlier. So the product to a power rule says we need to cube the 5 and cube the x to the 4th. And now we have both on the numerator and the denominator we have a power to a power again. So remember that when you have that scenario you multiply the exponents. And we're also going to simplify the 5 cubed since that's a number base being raised to a power. So 5 cubed is 125, and then we multiply the exponents on the x to get an exponent of 12, and we also multiply the exponents on the y to get an exponent of 6, again using that power to a power rule. And that's as far as we can simplify that, so we're done. Now we are going to look at dividing monomials, because eventually we're going to need to divide polynomials. So we'll start with dividing monomials, which is very similar to multiplying monomials. Remember, when we multiplied monomials, we would first multiply the coefficients and then multiply the variables using the rule of exponents. Well, we're going to do the same thing with dividing monomials. So we first divide the coefficients, which means we're really just going to reduce that fraction of the coefficients. Then we divide the variables using that quotient rule we just learned. So here's an example of a monomial divided by a monomial. So we need to first reduce the fraction 5 over 10, so that's the division of the coefficients. And then we divide the variables, and when we divide the variables we need to use that quotient rule which says to end up with a single base of x, and we subtract the exponents, top minus bottom. And note that that result will always end up in the numerator. And we can simplify that one step further. We don't necessarily need the 1 up there. And when we do the subtraction, 7 minus 3, we get an exponent of 4 on the x. Here's another example. It's a little bit more complicated. We have another variable here. So we need to divide the coefficients. Well, 6 divided by 2 is 3. And since that is a whole number, we don't necessarily need a fraction bar anymore because we know the variables are both going to end up in the numerator as well. And when we divide the x's, we subtract the exponents, 5 minus 3. Again, top minus bottom. And we divide the y's. We do the subtraction, 3 minus 1. So those exponents will simplify both to 2's, so we have 3x squared y squared. So now we're going to look at how to divide a polynomial by a monomial that's not, or a polynomial by a monomial. So here's a polynomial, a trinomial on the top, being divided by a monomial. So how we do that is we divide each term of the polynomial by that monomial. So we're going to divide the 5x to the 6th by the 10x, then we'll divide the 2x to the 4th by the 10x, and we'll also divide the 10x squared by the 10x. And notice that the signs in our polynomial on the top will go in between each of those divisions. Then now we just have 3 situations of a monomial divided by a monomial. So we simplify each term using those skills that we just learned, where we reduce the fraction of the coefficients. So 5 divided by 10 reduces to 1 over 2. And then we subtract the exponents on the x to get x to the 6 minus 1 on the top. Remember, that always goes on the top. Then we have 2 over 10 reduces to 1 over 5, and then we subtract the exponents on the x's, 4 minus 1. And then 10 divided by 10, you could cross the 10's out or put 1 over 1, and then the exponent will be 2 minus 1. and we simplify and we're done.